equations. Okay, we're going to be looking at all three types of equations that you might be asked to write. The complete chemical reaction, which is also referred to as the molecular equation, the complete ionic, and the net ionic. Now, we've seen already, as we talked about physical and chemical changes, that both physical and chemical processes can be represented with equations. Okay? But these three types of equations are going to be what you are asked to write. When you're asked to do the practice, you're going to be asked to go through all three steps, right? The molecular, the complete ionic, the net ionic. That will not always be the case. Okay, we ask you to do that so that you get more familiar with net ionic equations, and the hope is that you'll be able to go straight to net ionic. Okay, so we're going to look through a worked example. I've already got it worked out here, and we're just going to talk through it and do a few together. All right. This example, we've got aqueous solutions of aluminum nitrate and potassium hydroxide react to form the precipitate aluminum hydroxide and aqueous potassium nitrate. In this particular example, you are told what the physical states are specifically. Okay, aqueous, precipitate, aqueous. All right, when you write your equation, you will have to use those physical states. All right, so that's what I went ahead and did. I wrote my equation, I balanced it out. Now, I know we've talked before, how do I know, looking at a formula, what the physical state is? You won't, always. But we can use solubility rules to predict what the precipitates are going to be. Your yellow periodic table on the back, the reference side, has solubility guidelines. You don't need to have all of these memorized, but it will be helpful for you as you are working through problems to use this. Now, I'm going to pull up really quick the AP document that has the official essential knowledge from AP, and I want you to notice here this last little piece. This is from objective 4.7. This is types of reaction. But it says here that precipitation reactions frequently involve mixing ions in aqueous solution to produce an insoluble or sparingly soluble ionic compound. Okay. Then it says all sodium, potassium, ammonium, and nitrate salts are soluble in water. Those are the only 4 components of solubility rules that you are required to know. That's it. 4. Those are easy ones too, right? Sodium, potassium, ammonium, and nitrate. So when you are assessed and when you take the AP test, those are going to be the ones that you are expected to know are soluble, right? Anything else is beyond what you're going to be asked to do, which is great because that means you don't have to memorize all of these, right? So that applies here in our example, right? We've got aluminum nitrate, which will be soluble. We've got potassium hydroxide, which is going to be soluble, right? We've got nitrate, we've got potassium. So I've circled here in this second part, step 2, my 3 species that will be soluble. Okay, they're strong electrolytes. Along with soluble ionic compounds, strong acids and strong bases are also strong electrolytes. So you will need to memorize those 6 strong acids and strong bases that are on your reference sheet. Okay? Split up your ions. Make sure you're showing them as ions, and that requires charges. Okay? Do we have questions so far? All right. When we go to the third step, that's taking care of the net ionic, which means we're going to get rid of the spectators. So in this reaction, we see the nitrate is unchanged before and after. We see the potassium ion is unchanged before and after. So we're going to get rid of those from the complete ionic, essentially cancel those to get our net ionic equation. Now, you're going to see a pattern occur with precipitation reactions especially. Their net ionic equations will always follow the same pattern, which is ion plus ion yields precip. hydroxide. You'll see that. No matter what the precipitate is, no matter how many ions you have, right? So here we've got 1 aluminum plus 3 ion and 3 hydroxide ions. Okay, ion and ion yield the 1 precipitate of aluminum hydroxide. Yeah, see how that pattern is? Precipitation reactions and their net ionic equations aren't typically troublesome for students, but when we have acid-base reactions, which are another type of double replacement reaction, that's where some trouble occurs. So I want to actually skip example 2 on here because you had other precip reaction examples in the POGIL packet. I want to look at number 3 and number 4, which are going to be acid-base reactions. It's going to be important to be able to identify the strong acids and strong bases so that you can figure out whether we're going to have dissociation or not. So we've got aqueous solutions of hydrochloric acid and sodium hydroxide. Give us aqueous sodium chloride and water. So first thing, if you see hydrochloric acid, you should have a ding, 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 ding going off in your brain to say it's a strong acid. All right, strong acid here. And then sodium hydroxide also should have a little ding, 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 ding because that one is a strong base. There's only 6 of each that you need to know, strong acids and strong bases, so it's not really a lot. Okay. So that tells us those will dissociate completely. So this is actually a pretty simple reaction. HCl and the NaOH will be aqueous. We're going to get aqueous sodium chloride. And then water. What's the physical state of water going to be? Liquid. Water is not aqueous. It's what makes things aqueous. And if we're dealing with aqueous solutions, we're going to wind up with liquid water. Will liquid water dissociate? I mean, technically, right? We've got that equilibrium constant, Kw, but do we care about that here? No. So the liquid water is going to stay together. Okay. So when we dissociate these, I'm going to, just for clarity's sake right now, leave the physical states off of my ions, just to make my writing really clear. So we're going to go to the complete ionic. We're going to split up both of our reactants to H plus and Cl minus, Na plus and OH minus. NaCl splits to Na plus and Cl minus, and then that water stays together, right? So we're going to wind up in a strong acid, strong base reaction. We're going to always wind up with the same net ionic equation. Regardless as to whatever the spectator ions are, we're always going to wind up with the formation of water as the net ionic equation. What I almost always get year after year after year is students saying in a reaction like this that there's no net ionic equation, that no reaction occurs, which is absolutely not true. This is a neutralization reaction. Assuming we've got equivalent amounts of acid and base, we'll wind up with just water, no excess, right? That would hopefully be the goal. But just because it neutralizes doesn't mean no reaction occurs. Yeah.
So only aqueous, like ions, dissociate.
Got it.
Never liquid or solid.
Correct. Correct. Great question. Only aqueous solutions that are soluble. Now, that's why I'm going to go on to this last example, because we've got aqueous solutions of acetic acid and potassium hydroxide, which will give us aqueous potassium acetate and water. Acetic acid, is it a strong acid? No. Strong acids are HCl, HBr, HI. What's the next one on your list? Perchloric, HClO4, nitric, HNO3, and sulfuric, H2SO4. Anything else we're going to consider to be weak. So we've got HC2H3O2, which is going to be aqueous. It's going to be dissolved in water, but the majority of those acetate or the acetic acids are going to stay together, undissociated. Right? Yes, there will be dissociation that happens. Yes, it will be an equilibrium process. Okay, but that's not what we're concerned about here. This reaction is still going to go to completion because of the potassium hydroxide. Lots more of that to come with full-on acid-base unit in semester 2. Potassium acetate, which will be aqueous. And then again, we get water, which we know now we're going to have as a liquid. So, because, let me switch to red, this is a weak acid, this is a strong base, only strong acids and bases dissociate. So in our complete ionic, we're going to keep the acetic acid together, even though it's aqueous. It's a weak electrolyte. Potassium and hydroxide. Now, potassium acetate will separate. And then we get water. So this is one of those cases we were talking about before where we're only going to wind up with one spectator. In this case, it's going to be what? Just the potassium. Okay, so we're going to cancel the potassium for a net ionic. So we're going to get C2H3O2. Okay, our acetic acid plus the hydroxide, which will be aqueous. I should throw that in there here. Will give us the acetate ion. And then liquid water. This is an example where charge is conserved, even though we don't wind up with neutral or neutrality on both sides, right? We've got the negative charge on the reactant side from the hydroxide. Whoops. And then we've got the negative charge on the product side from the acetate. Questions at this point? Okay, let's go ahead and talk about representations of reactions real quick. Do super duper fast. Okay, this is just drawing particle diagrams, right? We've been working on this a little bit more. I don't know why AP decided to make it its own objective that you can use particle diagrams, but here we are. This is that same equation that I had worked out, the aluminum nitrate and the potassium hydroxide. I did two different particle diagrams here. One is for the complete reaction, okay, the complete ionic reaction, and then the other one is the net ionic. The difference is what? One has spectator ions, one doesn't. Okay, this first example is like what you saw in the Pogel on those first three reactions on page 1. Okay, the second one is just the net ionic. Now, is this one that I drew here for the net ionic ideal? No, because there's not enough particles to really show the physical state of the aluminum ion, right? Really, we need more to show that. Okay, I kept it here to the same ratio as the net ionic equation just for simplicity's sake. I want you to know that, when you're drawing particle diagrams, I don't care which type you draw, the complete reaction or the net ionic, unless I ask specifically for one or over the other, right? So in example 2, it does say complete reaction. In example 3, it does say net ionic, or the net reaction. Okay? Cool? Okay, when drawing the particle diagrams for these, you will need to have a balanced reaction first. So I would definitely start with that. This is going to be nitric acid and ammonia. So I'm going to just kind of write this over here to the side. So this is going to be HNO3 plus ammonia. And that's going to give me NH4NO3, which is going to be aqueous. All right, this is going to be a process that includes a strong acid and a weak base, which means that the nitric acid is that strong acid. It's going to dissociate into the hydrogen ion and the nitrate ion, where the ammonia is going to stay together. So I'm going to make a little key. Let's see here. I'm going to go, whoops. Let's do it this way. I'm going to go gray for hydrogen. I'm going to go blue. Try again here. I guess we don't want these as ions. It's going to be nitrogen, and then red for oxygen. Pretty classic coloring for those. And so I'm going to just kind of draw these out. Let's go, I don't know, like a couple of these. Let's go like 3. We want to make sure I'm following what I want for these. So let's go, I can get my coloring correct. 1, 2, 3 there. And then my nitrate ions, 1, 2, 3. I want to show those as NO3. These are going to be negatively charged. Okay, and then if I have 3 nitric acids, I also want to have 3 ammonias. So I'm going to go 1, 2, 3 there. All right, so because the ammonium nitrate is going to be soluble, we're going to show those 3 ammonium nitrates as those dissociated ions. So we're going to wind up with 3 ammoniums and 3 nitrates. So I'm going to start with my ammoniums, I guess. Doesn't really matter. 1, 2, 3 here. And then let's put on my 4 hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. And then we've got our nitrate ions. So 1, 2, 3. Stick those oxygens in there. Okay, wonderful. Now, the second example here, I guess technically the third, is going to be the net ionic reaction between the aqueous copper-2 sulfate and lithium hydroxide. Now, if we're told that copper-2 sulfate is aqueous, then we know that it's going to be dissolved. So we're going to go CuSO4, which will be aqueous, plus lithium hydroxide, strong base. And that's going to give me copper-2 hydroxide, and then lithium sulfate. Okay, these are going to be a situation where we're going to need our solubility rules to help us figure out which one is the precip. It is going to be the copper-2 hydroxide. Lithium is an alkali metal. Alkali metal compounds are going to be soluble. So what that means here is we really want to focus in on the formation of the copper-2 hydroxide. Remember, precip reactions, the net ionic equation is going to be ion-ion precip. So we're going to get copper-2 plus ion plus, which I didn't balance this one, did I? There we go. Plus the 2 hydroxide ions to give us the copper-2 hydroxide. Okay, so then I can draw these. I'm going to color code these again. I'm going to use different colors. I'm going to use a slightly different color of blue for my copper. And then in this case, because the hydroxide is going to stay together, we could just draw this as one single particle. I'll go ahead and demonstrate that here. I'm going to use like orange. Why not? And then this can be OH minus. This will be copper-2 plus. And then we can throw these in here. So I'm going to do at least a few of these. Let's go. I'm going to go 4 coppers. Okay. And then we'll go 8 hydroxides. 1, 2, 3, 4, 5, 6, 7, 8. which is going to give us that precipitate of the copper 2 hydroxide. We do want to show that this is going to be a precip. So I'm going to want to show those. 1, 2, 3. Oops, too many. 1, 2, 3, 4. I'm going to kind of rearrange that. Let's put these kind of like this. I'm going to put my 2 hydroxides on there. Now remember, we want to alternate these to show the attraction of these charges, positive to negative, okay, to show those particles. Okay. Now it is kind of a tedious process to go through all of these, especially if it's just asking you for the particle diagram, which is why on your practice you're going to be asked to go through all 4 steps. The complete reaction, the complete ionic, the net ionic, and a particle diagram.